Now, as you know, a very important part in chiller is expansion wall. So, as an instrumentation and control engineer, now how we look out in this into this particular type of words, keywords, that is how we can apply control for this particular type of important components in this chiller system. That is very important. One of very important component is expansion wall. And now I will show you here in front of you two diagrams, the left diagram and the right diagram. If I focus on the left diagram first, let me make highlight a marker. This particular two sections are here. Okay, in this left side, you can see now our instrumentation and control part now started over here. You can see the four blocks are easily we can now understand in a chiller. Now we are well aware with this. Right now you can have this evaporator, and then this output of evaporator enters into the compressor, and the output of compressor given to the condenser, and condenser is connected to the cooling water tower. In this particular upper side there is a cooling water tower, and then the output of condenser return through this particular block section, right? This particular section. So this particular section, if I highlighted you in this way, this is actually the heading, right? Expansion wall. So this is expansion wall, and then this output enters into evaporator. So how it can be we can have the PNID symbol of this particular wall here. Now there are two things in the left hand. If you see for this particular actuator part, right now you can easily see this actuator part over here, and this is main stem part. In any control wall there is actuator part and there is a stem part, and in this actuator part you can see there are two types of inlet to this particular wall. One main inlet, that is from the top side of the wall, is by this particular line. Okay, so this particular line is actually the vapor or pressure line. You can see by their notation, you can understand easily. This particular line, there is a pressure bulb connected over here, and this pressure bulb you can see connected at the end side of evaporator. Okay, so means that it monitors the discharge. We can say that the discharge pressure of this particular refrigerant that is given through the to the compressor is get monitored by one side, and equally you can see the other side of this particular wall or positioner. You can see some another sort of connection is there. So two types of connection you can see, and this is connected after this particular wall inlet outlet, and I may say that this may measure the temperature of this particular condenser temperature that enters after converting into liquid form into the evaporator. So this is general. I can have the highlight of this particular wall to you, and this can be their notation. It can be mentioned expansion wall. And in the cooling tower side also, you can see one more wall is connected to the cooling water system, this particular CWS. Okay, so in that line also, inlet line from the cooling water tower, one more wall is over there on the top side to regulate the coolant flow rate. Okay, that is also there, and that can be possible This can be possible by measuring the output of compressor. You can see the output of compressor that is detected here by particularly this, the output of compressor. Based on that, this valve get operated. So this is left side of this particular one type of valve, I can say, and in the right side there is another type of arrangement. It is not that always the same type of arrangement may be there. So another arrangement, you can see the same type of loop, evaporator is there, compressor, condenser, as well as this expansion valve in between. Along with this expansion valve, you can see there's one more valve placed over here. Okay, say additional valve placed over there. So this additional valve, solenoid valve, that can be used or it can be closed. The compressor is particularly turned off. If the compressor is down, this particular valve get activated, and that is connected before the expansion valve. But in this valve, you can see that now two types of different things get measured. You can see the one particular side, again the discharge pressure get measured, but at the incoming side also, the means the incoming side of evaporator, there is also the pressure measurement taken place. So in both the cases, you can see there is a measurement taken place. Now there is a small change over here. You can see both the side, the pressure differences get measured. So you can see that this is the pressure difference, but here one side is pressure, but another side is not pressure, but another side is temperature, I can say. So what we can have highlight of this particular thing, the control of the chiller's expansion valve depends on the type of operation. In installations with low evaporator drops, okay, sometimes what happens, there is a low evaporator drops, a superheat control valve. A superheat control valve is recommended. What that SCV is actually what? Superheat control valve. Superheat control valve, or it is a expansion valve, is recommended to the left side arrangement, while at low temperature applications where the process temperature is demanding low, in such cases the differential temperature type valve, what we can say, this particular arrangement differential temperature type valve gives more sensitive performance. Okay, so some more details are also available with this particular diagram. Now we can try to understand this from these particular sentences. Above figure of these two different types of designs illustrates some expansion valve design, right? Some means two types of design variation. On the left side of figure, a fairly standard superheat control valve is shown. That is, we clear out this particular thing. It detects the pressure at the inlet and the temperature at the outlet of the evaporator. What it is clearly written over here, it detects the pressure at the inlet and temperature at the outlet of the evaporator. So what we say, inlet, this is actually temperature bulb. Yes, temperature bulb is there, and here the pressure is get measured. So inlet of the evaporator is this, and outlet of the evaporator is this. If the evaporator pressure drop is low, for example, if the evaporator pressure drop is low, these measurements are an indication of the superheat. If this particular arrangement is connected to the controller and measurement part is also implemented over there, so they continuously detect the pressure drop. If that pressure drop is low, obviously what happens means that is saturation pressure and the temperature of the refrigerant, means that saturation pressure and temperature is one side, that to get measured. Particularly when this happens, when the pressure drop of evaporator is low, means that it is the indication of superheat. Superheat means that refrigerant is provided, refrigerant levels. Superheat means it is a refrigerant. The desired superheat is set by the spring in the wall operator. So what amount of superheat is required or refrigerant is required is set by the spring in the wall. So you can see in this particular diagram there is a spring in the wall, so that this wall opening and closing can be happen over there. Spring of the wall operator, which together with the saturation pressure in the evaporator oppose the opening of the wall. So depending on the saturation pressure in the evaporator, it decides the opening of that particular wall, or it indirectly we can say that it opposes the opening of the wall. The superheat filler bulb pressure balances these forces when the unit is at equilibrium and is operating at the desired superheat. That desired superheat nothing but what we are calling that as a refrigerant. And for example, we require to set that particular refrigerant with these particular values, that is our target or set point values, 5 degrees Celsius approximately, or there is some slight variation, 5 to 6, 5 to 8 in some books. For example, if the process load increases, what is process load increases? Demand increases. The load increases means the demand increases in the building, any building, maybe industrial building or any commercial building. It causes an increase in evaporator outlet temperature. Obviously what happened? If the demand in the building get increases, the demand means that there is more occupant requirements, more occupants present, and the requirement means the more number of persons were present. So obviously the outlet temperature obviously increase with that case. An increase in this temperature resulted in rise in the filler bulb pressure. Okay, so as the temperature increases, at the same time the filler bulb pressure also increases, which in turn further open the superheat control valve. So obviously as the outlet temperature is increased, so it is required to maintain that temperature at desired value, so that particular expansion control valve or superheat control valve opening will be taken place. Further opens the superheat control valve. As it opens, what it provides? More coolant, more liquid, more refrigerant it provides to the evaporator. Okay, so it is means the operation of that particular control valve is depending on the process load, and it is clear from this particular sentences is that as the process load increases, the valve also opens gradually. This greater flow of refrigerant, yes, because of this what happened? There is a greater flow of refrigerant liquid from the condenser to the evaporator, increases the saturation pressure. But what happened? As this enters into the evaporator, that increases the saturation pressure and temperature also. That also happens over there, and increased saturation pressure balances against the increased feeder bulb pressure at a new wall opening in a new equilibrium. So this is complete closed loop. So one part is affecting the other part. It is the same way happen when that pressure wall get opened. Obviously that increases the pressure and temperature inside this particular evaporator. As the control adjusts to the increased load, the evaporator pressure increases, but the amount of superheat is kept constant. So as the load increases means what happens? There is a more coolant that, or we can say that the refrigerant that is required to be passed through the pump to the building, to the evaporator. On the left side of the figure, the operation of the cooling water regulation valve is also illustrated. So there are two types of valve that already we highlighted. One more valve is there present on the top side, that is for the cooling water system, that is also mentioned over here. We can call that as a cooling water regulating valve. Okay, cooling water regulating valve is also there on the same diagram. What is the purpose of that valve? This valve maintains the condenser pressure constant and at the same time conserves the cooling water. This is the main purpose of that cooling water regulating wall that is connected in the left side figure of top section. The purpose is to maintain the condenser pressure constant, and at the same time it also conserves the cooling water to the condenser. At low condenser pressure, what happens? What happened? The effect of this pressure in the condenser, there is action required to be taken based on the changes in the pressure in the condenser. So what happened at low pressure? For example, there is a low pressure in the condenser, such as when the compressor is down. So pressure in the condenser is based on the output of compressor, because compressor is connected to the condenser. So when the speed of the this compressor get reduced or sometimes get down, we can say, then obviously the pressure in the condenser is also reduces. Then what happens? As there is no requirement of cooling water from the cooling tower, so what happens? The water wall closes. So obviously what action is required to take? Obviously that water from the cooling tower is required to close. Otherwise what happens? There is no compressor running and we are passing the water into the condenser. There is no meaning of that particular operation. It starts to open when that particular valve will open when the compressor is restarted. Okay, compressor is down, then the valve is closed. When the compressor is started or running, then obviously the pressure inside the condenser get increased and it is maintained constant after some time. So to make it happen, so obviously that water, that particular wall get open so that the water get feed to the condenser and condensation happens over there. And the discharge pressure reaches the settling value of the PCV wall. That wall is called as PCV wall. That is cooling water regulating wall. Or we can say that the name is given based on what basically it controls. Basically, it controls the pressure inside the condenser. So it is condenser wall or pressure control wall, we can say, or condenser wall pressure control also we can say, or cooling water regulating wall also we can say. The water wall opening follows the load by further opening at the higher load in order to maintain the condenser pressure constant, right? So based on the demand of the loads, so that opening can be taken place. So now we are much clear about these two types of wall from the left side diagram. This feature too can be incorporated in any one of the refrigerant unit. On the right side now, right? In the right side there is a small change that you can clearly, if I want to show you again the same diagram for this particular revision, you can say this right side, what change is there? Before expansion wall, before this expansion wall, there's one more solenoid wall. Okay, and what is the purpose of this wall? It closes when the compressor is down. So additionally, one wall is connected in series with this expansion wall, and the measurement type is different over here. Okay, now here differential measurement type arrangement is there. So differential temperature expansion wall. Okay, so this is differential temperature measurement taken place in this particular type with overload protection facilities also there. On the right side of figure, a differential temperature type expansion wall is shown. Okay, what is called that? Differential temperature type expansion wall is shown, which take advantage of the high temperature sensitivity at the low operating temperatures. So this particular arrangement is to improve the sensitivity against low operating temperatures. When operating at very low temperatures, for example, when operating at very low temperature, a small change in refrigerant vapor pressure resulted in a fairly large change in temperature. Okay, so there are conditions, high operating conditions and low operating conditions. Under very low operating conditions, a very small change in the refrigerant vapor pressure can result in large changes in temperature. So refrigerant vapor pressure is directly related with the temperature change. So there is a large change in temperature. For example, a 2.8 degrees Celsius temperature change, a small low temperature change, we can say that. A 2.8 degrees Celsius temperature change when a Freon 12 is the temperature of minus 73 degrees Celsius. You can see that this particular refrigerant, there are different types of refrigerant. If I take the names of the refrigerant, there is a ethane, means C2H6, there is a carbon dioxide that also acts as a refrigerant, there is ammonia, there is a methyl chloride, sulfur dioxide, all these, there are many types of refrigerant. So here one example of refrigerant is mentioned here, Freon 12. For example, 2.8 degrees Celsius temperature change when Freon 12 is at temperature of minus 73 degrees Celsius will result in 0.3 psig change in saturation pressure. Okay, so this particular change will result in 0.3 psig change in saturation pressure. The same what is mentioned here is given with the example also. Therefore, a more sensitive measurement will result if a thermal bulb is used to indirectly detect the saturation pressure in the vapor. So to have more sensitivity in this particular measurement, therefore there is implementation of thermal bulb, okay, that is indirectly detect the saturation pressure. Okay, so because this, there is an effect of change in saturation pressure, okay, vapor pressure, because of the change in temperature.